For this particular lesson, we're going to start talking about the behavior of some of these graphs of the functions that we've started to learn. And what you're going to see here is, or what you may have noticed up to this point, is now that we've learned upwards of 10 parent functions total, some of the new functions that you're dealing with have parts to them, if you will. No longer are they one continuous graph, but now they're being broken up into different parts, and so they're not actually two separate functions or two separate graphs. The individual parts all create one particular graph. Now, we're going to talk more specifically about what we call continuity. And you can see here by basic definition, a function is continuous if you can draw the whole function without ever lifting up your pencil. If you can't, that's considered a discontinuous function. So we have quite a few examples, new examples of discontinuous functions, like piecewise functions such as the greatest integer function, rational functions, or the reciprocal function. And so those are just a couple quick examples of something that you could see that would be discontinuous. Now, we want to introduce to you the different types of discontinuity, if you will, in this first video of this lesson. And so we've got a nice visual here that goes along with each definition. So we can see we have three types of discontinuity. We have infinite discontinuity, and so what's going to happen here is we approach a certain value in x, the value, the output value is just going to continue to get greater and greater and greater all the way to infinity. And so this is going to create what we briefly discussed in class is an asymptote. And so you can kind of remember that term. The second discontinuity that we're looking at is jump discontinuity. And this is more familiar to you through the form of a piecewise function. And so at this point you should have seen more than a couple piecewise functions that actually jump from one part of the graph to the other. Now, some piecewise functions have pieces of graphs that actually come together similar, such as like the absolute value graph, so that would not have any discontinuity. But many piecewise functions do have discontinuity, jumping from one to the other. And then finally here we have point discontinuity. In point discontinuity, we have a situation where something may be undefined, like in a rational function. And so the graph at a certain point would not be available to us, and so we would have to show that as kind of like a little hole in the graph. So that is a specific point that is discontinuous at. And so we have point discontinuity. So you can see the three major types of discontinuity that we can have. Now, the tricky part about this is how to figure out if a graph is continuous or not mathematically. Now, we've shown in previous lessons that we can visually determine a lot of these things like symmetry and in this case continuity, but visual is not always proof enough, and so we need to have mathematical tests that will test these certain conditions of continuity. And so you can see here on the second page of notes we have three specific tests that we are going to need to conduct on a particular function to determine if it's continuous at a given point or not, and so, or a given value for x. And so we're going to look at an example first and how we apply these three particular tests, and then we can work a problem of our own. Alright, example 1. Determine whether the function is continuous at the given x value. And so you can see here we have a fairly straightforward quadratic function. F of x equals 3x squared plus 7. That quadratic function is just going to move up 7 up the y-axis, and then it's going to be a little bit of a steeper graph with the 3 as a leading coefficient. And so we want to know if this thing is continuous at x equals to 1. So our first test is just to figure out at 1, do we have an output value? Okay, and so is it defined at that value? And so if it is, in this case, the function is defined at x equal 1, the output value is 10, and so in this case we have the actual point on the graph of 110. And so we know that it is defined at x equals 1. So that means that we've passed the first test for continuity at that value. Secondly, we have to determine if the function approaches the same y value from both the left and the right side. So if I had a visual test of this, let's try that again. Let's just assume that this is our function, and at 1 we want to know if it approaches the same value and from both sides. And so basically, do the values from this side approach the same as they approach from that side? And so what we're looking to do is to see as small as we can get, how close we can get to a number without actually hitting that number. So we are going to use some t-charts, or some tables if you will, and instead of using 1 exactly, we're going to use the x values of some decimals that get really close to 1 but are not actually 1. And so you can see the two examples we have here, and if you look very closely, they both seem to get really close to 10, and closer to 10 the further our decimal goes out. And so that's going to actually give us a confirmation on our second test of continuity. And then last but not least, the third one is the y value that the function approaches from each side is the f of c. So it is approaching 10. It's approaching the same value, which is our second test. The third test is it approaching 10 specifically? And it is. And so we can say that this graph is continuous at x equals to 1. So that's a good example. For the next video, we're going to come back and look at sample problem number 1. So go ahead and take some time to work that, and then come back and watch the next video to see if you got it right.